Okay, welcome everyone to my presentation. So today we'll be talking about comparative analysis of micro and mini channel flow boiling using classification and clustering algorithms. I know it's quite the mouthful, but it's an exciting journey that we're going through. And this project was done in collaboration with University of Westminster, Nottingham Trent, and of course my university, University of Hertfordshire. So before we dig in, just a quick background of what we were talking about today. We're just going to talk about the background of the study, what the problem was, how the materials and methods we used to solve it, the results we got, and some further work that we are planning to do in the next couple of months. Again, before we go into the presentation, just a bit of who I am. So I'm doing a PhD in microchannel flow boiling and using machine learning algorithms, and I'm currently finishing as well as I'm a visiting lecturer at the University of Hertfordshire. Previously, I've done projects for Rolls-Royce, Hitachi Automotive Systems, National Center of Motorsports, and I'm currently doing around 4 projects for European Commission, Royal Society, and EPSRC. Phew. Just trying my best. Just trying my best. Okay, so when you hear the word microchannel, all the good presentations that we had previously, we spoke a lot about the grand scale of it, landing aircrafts, talking about buildings, house sizes. But in my case, I work in microscale, nanoscale. So the type of models that we use, so this is a typical microchannel, one of the most basic ones that we use in our field. And microchannels are one of the most active research fields because it's aligned with EU's 2050 sustainable goals and also UK's net zero goals. So microchannels are basically very narrow channels where you through the inlet, you send some kind of liquid. It could be water, it could be nanofluids, it could be refrigerants as well. And the reason we use it is because to cool stuff like electronic chips, high-power LEDs, high-power lasers, and so on. And microchannel was actually first come up with by 2 people called Tuckerman and Peace, and they were working for IBM, and they first used it to cool electronic chips. So one of the issues with microchannel is because we're working in very, very small scale, the type of stuff that can go wrong, it's a lot. And the type of methods that we can use to make it good is also a lot. So that's the reason efficient thermal management and hydrothermal performance are crucial for the successful implementation of the microchannels. So here's a video of how a microchannel works. This may look like it's happening quite fast, but this has to be slow mode because the changes that occur within a microchannel in terms of bubble is quite rapid. I have to slow this video down just so you could see it. So in terms of our project, we're mostly focusing on the heat transfer and thermal management using the flow boiling, which is you heat up the source, which could be an electronic chip. In our case, we're using Intel Xeon processor chips. And as you can see, there's rapid changes that's happening, and we want to classify the different types of bubbles and flow regimes that's occurring. And for that, we need to do experiments, and at the same time, we need to implement pattern recognition and machine learning techniques to classify it. And one of the reasons that we want to classify the different flow regimes is because every regime has different rates of heat transfer, every regime has different types of pressure drop, and all this is related to the energy consumption of the system. And because we're working with sustainable energy related research in our lab and for EU, this is something that we want to maximize the efficiency of. So initially, when we started looking into the flow regime, we have 4 types of different flows that we want to segmentize and classify, because when you're watching the video, a lot of things were going on. But in holistically, there's only 4 types of flow that we can categorize in and label it. The first one is the bubbly flow. The second one is the slug flow. Third one is the adenal flow. And the last one is the mist flow. If you look carefully, some of them may look similar, but due to the data that we get from sensors, they are quite different, and the heat efficiency is quite different. So classifying all these images accurately. However, when I say accurately, it also needs to be efficiently and in a less time consuming way as well. Because in our field, we want high accuracy, but we want to, I think it's in any field anyway, high accuracy using the least time possible, because we want to up our product development cycle. So what's the problem, as I mentioned, in terms of the problem itself, as I mentioned, a lot of it looks similar. So when we're classifying it manually, there's issues with subjectivity, interpretability, and how are we generalizing all these flow patterns across systems, across different applications is one of the issues as well. So that's the reason we have the scope to investigate new methods that we can use to classify these flow boiling patterns and recognize the flow boiling pattern as well. And when we looked into the literature, we saw the gap, and we chose a CNN clustering combined approach that we're going to do here, and to provide the impact, which would be getting generalizability in this application. So how we achieved this? So initially, we achieved it using a 4-stage method. So we checked what's out there and what people are doing. So we found that there's 2 methods of classifying these kind of issues. One is the direct method, which uses high-speed photography and uses X-ray tomography. And the cost of buying this equipment is quite a lot. One camera can cost 60,000 pounds, 80,000 pounds easily. However, we wanted something which is cost efficient and time efficient as well. So we checked all the methods and we came up with our one. And in terms of the other methods that which is indirect, we can use something called time frequency analysis. And some machine learning algorithms have been used previously as well, but the accuracy levels have just not been that good. It's around 70 to 75. Some have reported 80%. So in the second stage, we set up the experiments, we collected the image data, and the third stage, we labeled it and tested the feasibility of our models. And again, the last stage, we pretty much refined and retested. So I'm just going to show how the experimental test rigs looks like. So basically, what you saw earlier is in terms of microchannel, that's what it is. This is a scaled out version because we want to take more photos. So, however, this still counts as a microchannel and a mini-channel as well. And I know there's a lot going on. I'm just going to explain it as quickly as I can. So there's a lot of sensors in there. The flow starts in the tank. It goes through the pump and does a loop through the pressure transducer and goes into the microchannel. Here we use a fan just to cool it, because otherwise, if we keep increasing the temperature, at one point the pressure drop and the heat loss just becomes great. And yeah, so this is like a closed circuit loop, and we're using, in our case, deionized water to complete the loop. Now, we have all the background to the project. Now, what we did is we initially, because we want to classify and recognize the patterns, we created our own version of a data pipeline. So from the experiments that you just saw, we collected a chunk of data. In our case, we collected 1,600 images. And using the 1,600 images, you've done some random augmentation, which you can see a snippet of it in here. Initially, we tried with different types of augmentation. We added Gaussian blur, we added filters, we added different types of zoom, crop. But the issue with that is because we're working with very small micro bubbles, the more you distort the images, the more random the predictions using machine learning or any other deep learning method gets. So we want to keep the features as much as we can, but at the same time, we want to reduce the data as well, because each image could be 8 MB, 10 MB, and if you have thousands of them, we're working with gigabytes of data. We want to make it more time efficient and as well as more accurate as well. So that's the reason we started doing our CNN and the clustering algorithm approach. So what we did initially, we manually labeled all our data based on experts and our own expertise, and that was our baseline. Using the baseline data, we trained a classical CNN just to check the accuracy of the CNN against our, you can call it ground truth or the initial manual label data. And that CNN was then after the augmentation, created a database. And that database we checked with 4 different types of clustering algorithms, and I'll talk about it slightly later down the presentation. And that clustering algorithm classifies all the data into 4 different types of flow regimes that I have shown earlier that we want to classify and recognize the pattern flow. And again, as you can see, it collects a loop, and this is actually a semi-automated pipeline because we have to run the code every time for every run that we do. So that's the reason it's semi-automated, and that's what we want anyway, because it depends on the experiment of how much data we want and how much classification we want as well. So that's the overview of the architecture, and I'm just gonna move to our next slide. Yeah, so using that, as I keep repeating that we want time efficient, so there's always a trade-off in engineering. I know everybody is from computer science background. My background is more towards mechanical engineering. So we have to find a trade-off between accuracy and the amount of time it takes. So in this case, what we did was, so we trained just to see how it's working. We trained a base CNN model just to see how the accuracies are. Then we added 2 hidden layers. And the third thing that we did to the 2 hidden layers, we pre-trained the model and we run the data again, just to see how it's working. And as you can see, when we were pre-training the model, the training and the validation accuracy was nearing around 90 to 80%. And we use this as our baseline to compare our clustering algorithms. Now, so these are the results that we got from the clustering algorithms. And as I mentioned earlier as well, the regimes, we want to get rid of the subjectivity and the generalizability of the models and make it standardized so that when it goes from one system to another, someone say, oh, why is this a slug flow? Why it can't be an annular flow? So we want to standardize it across the board so that there's no confusion. So in this case, so we took an image of the exact same point and exact same time to check how the different clustering algorithms are recognizing the patterns and classifying it as well. So in our case, even though there's 4 different regimes, we're mostly focusing on the slug one and the annular flow because that's where the maximum heat transfer occurs. So in this case, if you can see, when we use the k-means of the Gaussian mixture model had quite similar clusters. However, in terms of the bubble coalescence, if you see the image where with the red circle, the Gaussian mixture model can identify small differences between the bubbles. Whereas if you go to the hierarchical clustering, it just at the same exact instant, it takes something which is further down and detects the images which are, for example, have collapsed. And if you go back to the annular one, as you can see, if you look correspond to the clusters as well, in this case again, hierarchical clustering is more suited towards bubbles which are misflow rather than annular or slug flow. So when we check for the same exact moment or the cutoff point of where it's making those clusters, Gaussian mixture model it tends to be better in terms of recognizing the differences between the patterns itself. So that's the image. We're just going to talk about the performance comparison. And in terms of the performance comparison, what we did after we made our predictions, we created a confusion matrix. And using all our categorical data, we converted, we one hot encoded it to make it into data that we can compare against our base data, just to check how much it's basically accurate compared to how much we want. So in this case, I personally don't like using mean, median, standard deviation, but in this case, we have to use it just to check how many correct predictions we're getting compared to our base data. And as you can see, even though the base CNN performed very well in training, in terms of when we're validating the data, it was about 77%. So it's quite obvious there's overfitting issues with the base CNN. In terms of the k-means, again, the training validation is good, but the validation is quite low. So if you look at the data, GLM which is the Gaussian mixture model, had the best performance in terms of standardizing the data itself and having the less overfitting, because 90% of the training accuracy is what we achieved. And in terms of validation or testing, 88%. So there's a very good agreement with it. Hierarchical clustering was okay as well, but it's around 74%. And in our case, anything over 75 to 80% or 85% is what we're going after. We can obviously refine, retest, add more data, and reach we have done tests where we have reached 88 to 90%, but however, it takes a lot more computer power, a lot more time that we don't want to have. And so just some of the key talking points. So if we go back to the base CNN, as I mentioned, there's high training accuracy, and the standard deviation between the prediction as well, it's quite low. It's actually one of the lowest, but it is kind of expected because it has used the manually labeled data set that we want. And in the k-means ones, again, it's one of the worst performing one because k-means in general uses the Euclidean distance. So when it's classifying different images, the Euclidean distance method doesn't work that well. However, the GMM, the Gaussian method, using the unlabeled data, actually was our best performing one. And this is, in a way, we were expecting 80%. It kind of surpassed our expectation a little bit. Even when we did a second run, it was around 87, 86%. But we like to mention our best one. So around.
Don't we all?
Don't we all, of course. So yeah, again, the hierarchical one was like, it works, but we rather use the GMM method. Okay, so I'm not quite proud of this video because I had to use my phone camera to collect the video. So the microchannel that we saw initially, that's like a very simple one. This is a very complex structure of microchannels. And as you can see, there's a lot going on. The bubble sizes are different. The transitions are different. So whatever we have done here today, for future work, we're going to implement the same using in these complex microchannel systems. And yeah, and hopefully it's going to be done in the next couple of months, hopefully. So in conclusion, we have created an efficient, streamlined generalization data pipeline that we can use across our experiments, and someone can actually take this and use it in their experiment to check how the generalizability is. And because we reached around 88%, as I said, it's what we want. Even if we got 80%, we'd be happy with it. And it's semi-automated and it's catered to your application as well. As I mentioned earlier, because we want it semi-automated. And the comparative analysis of clustering, this combined clustering CNN approach that we have done, when we're checking the literature, no one has actually done it before, like in this manner. Obviously, people have done deep analysis in other parts, but not in this specific application. And sometimes, you know, it's better to keep things simple rather than throwing the kitchen sink at it and just expanding the problem. Yeah, and this is what we want. And again, this solves a real world application problem, and it's generalizable when we're using different lighting, different backgrounds, or different orientation of microchannels, which we'll be working with our future work that I mentioned. And these are some of the work that I have done. Some of the names may look familiar, and this is in our area, just in case. Yeah. And because this project was done across 3 universities, we have a lot of diversity going on. We have Bangladesh, we have Greece, we have China, and I realized this conference is initiated from Chile, so I added some Spanish as well. Yeah, so thank you.